Okay, we'll continue on with our material on compressible flow. So what's on the board now? We covered last time. We derived those three equations for a perfect gas, isentropic flow, the subscript T naught, P naught, rho naught. That's a condition where the velocity of the flow has been brought to rest, the velocity is zero, isentropically. The rho, the P, the T is anywhere in the flow field. And you've got a choice. Either you can use the equations, or if you'd rather, you can go to table B1. I'll put that over here, table B1. Back of the book, okay? And that table gives the following. Mach number is the first column. P over P naught, T over T naught, rho over rho naught. There's another column which we'll talk about later, but just so you know what it is in the table, it's A over A star. We'll talk more about that column a little later on. So you can see the similarity. The equations, what you'd like to have to use the equations, you'd like to have the Mach number. Flow in a pipe, what do you want first? I want the Reynolds number. It's the most important. Compressible flow, what do you want the most? I want the Mach number, because the Mach number will give me T, P, rho. So this is the equation. There's the K of the gas, just so we know the K of the gas. K equal 1.4. Is that a big restriction? Yes and no. K 1.4 for air, nitrogen, oxygen, carbon monoxide, nitrogen oxide. So K 1.4 for a lot of different gases. Carbon dioxide, nope, won't work, can't use it. You got to put the right value K in. But if K is 1.4, you can sub K in these three equations, and you end up with the equations for the T naught over T in terms of just the Mach number, 1 plus 0.2 Mach number squared, 1 plus 0.2 Mach number squared to the 3.5 power, 1 plus 0.2 Mach number squared to the 2.5 power. So if you've got a gas with K of 1.4, you can use those last set of equations. We'll be dealing mostly with air in this introductory type course, but it could be any of these gases with a K of 1.4. You can use those equations for any of these gases. If it's not one of these gases, okay, helium, carbon dioxide, then use this one. Now you can go over here and use that table if you want, table back of the book. Mach number 0, 1.0, 0.0, 1.0. Mach number 1, 0.5283, 0.8333. Density ratio 0.6339. And then the Mach number goes to 2 to 3 to 4. So you can use the table, or you've got the equations. So that kind of choice is up to you. Notice they're flip-flopped. T naught over T, T over T naught, okay. Now, the problem with, not a problem, when you use table T1, you just have to make sure that K is 1.4. Don't use it for a gas where K is not 1.4, obviously. It's only meant for gases K 1.4. Now, another thing. At a location in the flow field where the Mach number is equal to 1, okay, sonic speed. Speed of sound, c, the square root of kRt. The Mach number is v over c. So if you go in the flow field, if there's a point in the flow field where the Mach number is equal to 1, then what we do to differentiate that, just remember that these guys are stagnation. What's this guy called? Stagnation, temperature, stagnation, pressure, stagnation, density. Subscript 0 means stagnation, where the velocity is 0. Fluid is brought to rest isentropically. At this point, the Mach number is 1, so you can go ahead and put those guys, we'll leave in terms of K first of all. P naught star over P naught, and T star over T naught, and rho star over rho naught. So this is 2k plus 1 to the k over k minus 1. This is equal to 2 over k plus 1. This is equal to 2 over k plus 1, k minus 1, 0.5283. This guy is 0.8333, and this one is 0.6339. So that's where the flow, if it does reach Mach 1, that's the value of, this shouldn't be, the value of the pressure at that location, the temperature at that location, the density at that location. Here they are here too. 5283.8333.6339. Okay. Where the Mach number is what? 1. Mach number is what? 1. There's the equation. If k is not equal to 1, use this guy. If k is not 1.4, use this guy. K is 1.4, you can use him. K is 1.4, you can use table. K is 1.4, you can use this. Okay. But don't use that table if k is not 1.4. Okay, so that is added then to your library to go to if you need to. Those are the equations you might need, and we will use them and the problems. But we're going to take a look now at in a duct, a changing area duct. So we're going to consider now a duct in which the area varies. So we'll take the picture. I'm going to put it over here so that I have more room. So here's a duct where the area is changing with X. We can measure X from somewhere here. Okay. And recall the Euler equation. That was in chapter 4 of our text. The differential form of that looked like this. Okay, V dV plus dP over rho equals 0. We also have continuity equation. And that's rho A times V equal a constant. Go ahead and take the differential of this, rho A dV, rho V dA, A V d rho equals 0. Take the differential of that product. Okay, then we're going to divide through to get dV over V, divide through by rho AV, divide through by rho AV, dV over V, dA over A, d rho over rho equals 0. Now we go ahead and use what we had from speed of sound, c equal the square root of dP d rho, c squared equal dP d rho. Okay, so there's my dP d rho, there's d rho, there's d rho. So go ahead and put that guy in there. Use this in equation star. Equation star is this guy. There's dP. dP is c squared d rho. So replace the dP with c squared d rho. And we get this. Okay, both those guys go into there. And then take it one step further. And let's see our final equation there. Oh, there it is. We get dA dV. So that is close to our final equation. And then we want to do one more thing to it here. Oh, there it is. dA dV, let's see, I think I want to make that a little bit simpler, so let me check what I want to write that. That's okay, dA dV, yeah, that's fine. Okay, where did it come from? Euler equation, energy. Continuity here. Definition of the speed of sound here. Put them all together, what do you get? This guy. Okay. From this guy here and taking this guy here, dV, dA, d rho, you get this guy. Okay. dP, d rho, dP, d rho. Substitute in dP, d rho minus V dV over C squared. Okay, there's a C squared right there. There's a minus sign right there. There's about 3 lines of algebra missing, but you can do that. Okay, so now we've got this. There's the equation. Let's put the equation back over here. So we have dA dV is equal to A over V. Mach number squared minus 1. Okay. If subsonic, Mach number less than 1, subsonic flow. dA dV equal A over V times m squared minus 1. This quantity is less than 1, or less than 0, negative. Just put it down there as negative. Negative. Mach numbers 0.3, 0.09 minus 1, negative. What does negative mean? It means the change in area with respect to velocity is negative. Okay. So it means if I've got a situation like this, velocity here, okay, if the area gets smaller, the velocity gets larger. Okay. The right-hand side is negative. Okay, check it out. The area is always positive. The velocity to the right, positive. The parentheses, negative. Okay, the right-hand side is negative. Go over here. The differential area gets smaller. dA gets smaller. This side is negative. This side is negative. What does dV have to be, positive or negative? It has to be positive, because a negative divided by a positive is going to give me a negative sign over here. That's a negative sign. Now the signs match. What does that mean? As the area gets smaller, the velocity gets larger. Well, you know, I knew that before I did all that mathematics. If I want to go out in the backyard or in the front yard and wash my upstairs windows, if I turn the tap on, the water spigot on, with just a hose, the water comes out and it goes down like that. It might go 3 or 4 feet forward. That's all the further it goes. Oh, but now I'm pretty smart. I go buy me a hose nozzle and I put it on. Now I can wash the upstairs windows. Because what did the nozzle do? It made the velocity larger. And how did it do that? It made the area smaller. You know, we all know that. That's Life 101. Okay, you put the nozzle on the hose that goes further. Yeah. What do firemen do? They put the nozzle on the hose that goes to 3 stories tall. Yeah, I know that. Okay, but now we play the compressible flow game. dA dV, A over V, m squared minus 1. Supersonic. Okay, Mach number greater than 1. dA dV A over V m squared minus 1. Mach number's 2. 2 squared, 4. 4 minus 1, 3. Positive or negative? Positive. What's the area? Positive. What's the velocity to the right? Positive. What's the sign of the right-hand side? Positive. Okay. What's the area do? Get smaller. dA is negative. Uh-oh. I want it to be positive because the right-hand side's positive. I got a negative sign over here. Guess what the velocity does? It goes down. It goes down. Negative divided by negative is a positive on the left-hand side. This guy's positive. The signs match. Conclusion. Area decreases. V gets larger. I'm sorry. Smaller. Just the opposite of the subsonic. You got to shift gears and say, uh-oh, we're in the compressible flow chapter. Strange things happen. As I make the area get smaller, the velocity goes up. And it's hard for people because our real everyday life is not compressible flow. It's incompressible flow. The air in this room coming out of the HVAC duct is incompressible. The water in the hose in your backyard, it's incompressible. We very rarely deal with compressible flow in everyday life. So you got to shift gears now because things are totally opposite, and I mean totally opposite. All right, let's take one more. If I do reach sonic speed, if Mach number equal 1, then I have dA dV equal 1 squared, 1 minus 1, 0. So that means that dA has to be 0. That means to get sonic flow here in a changing area duct, you have to go through a local minimum with the area. dA equals 0. The area does not change with x. Okay, so 3 pictures. Sonic, subsonic, supersonic. So if I have a reservoir, it's a large reservoir. And in that reservoir, let's just say air for the sake of a fluid. Air, that fluid's at rest. The fluid velocity in the large reservoir is at rest. Okay, if it's at rest, I'm going to attach the subscript 0 to it. T0, P0. So in the reservoir, the stagnation, the temperature and the pressure are called the stagnation temperature and stagnation pressure. Okay, that's my reservoir. Now, I'm going to build me a supersonic wind tunnel. Okay, supersonic wind tunnel. I've got to accelerate that flow from 0 because the velocity in this large reservoir is 0. Here we go. Okay, it's going to start off to be subsonic. If the velocity is 0, the Mach number is 0. Okay. Let's start to make the velocity get larger. If I want to get the velocity larger, I make the area get smaller. Okay. Velocity is getting larger. Mach number 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. I'm getting close to sonic speed. So I go through this, and if I design it right, I might get sonic speed at that point. I don't have to, but if it's designed, as a supersonic nozzle, I will get Mach number 1 there. So I'm going to say that I get Mach number 1 here. I'll just show you. Here's another one here. I'll make it up. Mach number equal 0.5. Okay. I'm not supersonic yet. I just reached sonic speed. I want to go faster. Okay. Mach number, now supersonic. If you want V to get bigger, you make the area bigger. Okay. And now you reach a Mach number which is supersonic. And then probably you end up out here in some back pressure region. This is called the back pressure, P sub B. This is called the reservoir pressure, P naught, T naught. This is the back pressure, PB. That's where the nozzle exhausts to the local conditions. It's also, this is called the exit area, just so we know. This is the exit area. This is called the throat area. That's called the reservoir. Now, it doesn't have to go supersonic there. Under other conditions, I'll make something up here. You might go to a Mach number of 0.9. You didn't reach sonic speed, and now it goes back to subsonic, 0.7. So, Mach number 0, 0.2, 0.4, 0.6, 0.9, 0.8, 0.7, 0.6. That's not a supersonic design nozzle. So, but if you want to reach supersonic conditions in that nozzle, it might be a wind tunnel for a certain aircraft, then this Mach number is 1, and this would be 2, and that now is called a supersonic design nozzle. And we'll get into that a couple more class meetings. Just so you know, though, how do things change as the area changes for subsonic, for supersonic, and to reach sonic speed? That's the conditions you have. All right, now, there are two possible kind of nozzles. This one, by the way, is called a converging diverging nozzle. Converging part, diverging part. We're going to study that a little later, but before that, we're going to study just a plain converging nozzle. Okay, so let's look at a converging nozzle. Just a little bit of a look ahead. We're going to find out later on that it's possible to have a shock wave in the diverging part of the nozzle. There could be a shock wave there. And a shock wave, the Mach number here might be 2, and let's just put it this way. This would be supersonic. When you go through the shock wave, it goes back to subsonic. So yeah, it's going to get a bit complicated, but that's another day, okay? But there could be a shock wave in the diverging of the part of the nozzle there. Let's go to the converging nozzle. So for the converging nozzle, all we do is we take the picture to the left of the paper. That's a converging nozzle, okay? The reservoir conditions are still P naught and T naught. It exhausts into a back pressure region, P back. Okay, let's see, I think that's all we need. The flow is going to be going this way, of course. This pressure here at that point is called P exit. This is the exit, the nozzle. Okay, I think that's all we need in our picture. Okay. So if we have this, first of all, is it ever possible to have supersonic flow in this nozzle? No. Okay. Number one conclusion, a converging nozzle will not have supersonic flow. Could we ever get Mach number one? Oh yeah, dA dx is 0 here. It goes through a local minimum, dA dx is 0. There's a possibility that we could reach Mach 1 at the exit under some conditions. Okay. Now, what's the Mach number here? 0. What happens now? The flow starts to accelerate. Why? Because it's subsonic flow in a converging nozzle. The velocity has to go up. Okay, velocity goes up. Let's look at what happens in a graph like this, kind of explanatory. We're going to plot x here. We're going to plot, this is the exit. It's also the throat. Not quite the throat. It's not, it doesn't go beyond that point. We'll call it the throat area too. This is P over P naught. When x is 0, we're in the reservoir. If you want, we're measuring x from where the reservoir ends here. X is measured from here. X equals 0, reservoir conditions. What's the pressure in a reservoir? P naught. P naught divided by P naught is 1. All right, we start at 1. The way that you can control this is some pictures show this on it. There's some big kind of valve back here. Okay. And we can open and close that valve. If the valve is closed, no flow goes through the converging nozzle, of course, if the valve's closed. Then what's the pressure everywhere here? P naught everywhere. P naught, P naught, P naught, P naught, P naught. Because there's no flow. Now you crack the valve open. Some flow starts to go through. Does the pressure change now? Oh yeah, of course it does. Open the valve some more. Does the velocity change now? Oh yeah, more flow, more flow. Does the pressure change? Of course it does. Okay, so we play that game. To vary the flow rate, open or close the valve. This one up here is the valve closed. The pressure everywhere, for every x value, the pressure is P naught. Then we crack the valve open and we get flow and the pressure goes down. We crack the valve some more, we get a higher flow rate, and it goes down. We crack it some more until, oh boy, now we've got Mach number at the throat or the exit equal 1. We've opened that valve enough to create a velocity high enough to reach Mach number 1 at the exit or throat of the nozzle. Okay. So we go to our table B2, B1, pardon me, table B1. We'll assume the gas has a K value of 1.4. Assume it's air if that's normal. Mach number. Okay. P over P naught. T over T naught. I might have that guy reversed. Let's see. Yeah, that's okay. And rho over rho naught. We don't need that. Go down here to a Mach number of 1. Read off P over P naught. Mach number is every 0.1 in there. 0.5283. Temperature there, 8333. Yeah, 8333. Okay. When I get to here, or I first reach Mach 1, P over P naught, 0.5283. But what pressure is that? That's the pressure where the Mach number is 1. And how do we denote that? We put the little asterisk there. That's P star over P naught. The pressure where the Mach number is 1. If it's not K 1.4, then that's not the magic number. Use the equations, which I erased. Use the equations to find that if K is not 1.4. Now I reduce the pressure still more. I open the valve more. I want more flow through. Now I get an expansion wave outside the nozzle. Reduce it still more. I get another expansion wave outside the nozzle. Not in the nozzle, outside the nozzle. They're called expansion waves. Notice when I reduce that, this is the back pressure. This is the exit pressure. When I reduce the back pressure, the exit pressure doesn't change. Okay. So no more flow goes through the nozzle. Okay. So that's called if P back over P naught is less than 0.5283. No more mass flow passes through the nozzle. Because that pressure stays at that magic number, 0.5283 times P reservoir. Even though you reduce the back pressure, nothing happens in the nozzle. The nozzle didn't know you changed the back pressure. Why? Well, because you reach the speed of sound. It's like cutting the telephone line. Once you reduce this, that pressure can't work backwards and tell the nozzle, hey, I've reduced the back pressure. Increase the flow. No, because you've reached the speed of sound there. You've cut the communications line right there. The nozzle didn't know you reduced the back pressure. It stays the same no matter how much you reduce this back pressure, which means it passes the same mass flow. So now you've got the maximum mass flow that the nozzle can pass. So we can put it over here, I think, to make more room. By the way, it's called choke flow. It can't pass any more flow rate. So m dot equal rho AV. There's A1. Doesn't matter where you are. The mass flow rate's rho AV. Rho 1, A1, V1. At the throat, rho throat, A throat, V throat. At any position, any x value in that converging nozzle, that's the equation for mass flow rate. I don't care where you are. But now, let's say you've reached the magic number 0.5283 at the exit plane. Okay, now I have the maximum mass flow rate. Now I've got, if Mach number at the throat or exit equal 1, then I've got the maximum mass flow rate. Rho star, A star, V star, which is the speed of sound. And we had the equations here earlier. Here they were over here. There they are. So what do? Let's see. I need rho star. So there's rho star. 0.634 times rho naught. I need the speed of sound. What's that? The square root of KRT. What T? T where the Mach number's 1. T star. There, 833 in there. A star, exit area, throat area. So when I'm done, this is what I get. So you've got different choices of how to find mass flow rate. I don't care where you are, put your pencil point anywhere in here. The mass flow rate is rho AV. But if you've reached Mach 1 at the throat or exit area, then that's the maximum mass that the nozzle can pass. Then use this one, because all you need is P naught, which is usually given, T naught, which is usually given, and the area of the exit, which is usually given. That's the easy way. I mean, you want to do it you can do it this way. But the easy way is to use this equation as long as you know the Mach number is 1 at the throat. And how do you know that? You calculate this guy right here. And if he's 0.5283 or less, you know you've got Mach 1 at the throat. If he's greater than 0.5283, you're on that curve, or that curve. Did you reach Mach number 1? No. Is it choke flow? No. Can you use this equation? No. Then what do? Use one of those guys, okay? Because it's not choke flow. Okay, so that's a good stopping point today. We want to get the first midterm back to you. So we're going to stop here and continue on with this then on Wednesday.